Okay, I'm going to start making my video as soon as you're done with the kitchen. As soon as you're done with the kitchen, I'm going to start my video. The first question from the additional problems. I wonder what's working here. Let me try this again. Okay, so the first question from the topic 13, additional problems, is about exponential decay. Given the quantity Q of t exhibiting exponential decay is described by this function, Q of t equals 2000 e to the negative 0.06 t, where t is measured in years. We're going to answer the following questions. What is the decay constant? So the decay constant is going to be the number in front of the t. And that's way too big. Let me try that again. Trying to zoom in on this if I can. Okay, that's a little bit better. Okay, I'm ready to record. Okay, these are the topic 13 additional problems. The first question is, we're given this quantity Q of t that exhibits exponential decay is described by the function Q of t equals 2000 e to the negative 0.06 t, where t is measured in years. And we want to answer the following questions. What is the decay constant? So this is just understanding the structure of these quantity models, exponential quantity models. And so we want to make sure that we're really clear that the first term that goes in front of the E is the initial quantity. And the second term, oops, oh, that's not very good. Let's try that again. The second term that goes in front of the T is our decay constant or growth constant, depending on whether or not there's a positive or a negative. So if there's a negative, we call it a decay constant. Okay, so the answer to A is just negative 0.06, and it is a quantity in years. And I remember I was telling you that the rate has units that always are in per units of time. So this is measured in years, and we can see that here. Because we're told that t is measured in years. Okay, so then what quantity is present initially? And again, this is just going back to understanding the general format of what these equations look like, which if you remember is Q of t is the initial quantity, which we call Q naught, e to the negative kt if it's decay, and if it's a positive k if it's growth. All right, so in this case, the Q naught, or the initial quantity, is our 2000. Okay, now we're going to complete the following table. So this is just simply plugging in for t. All right, so you want to make sure that you can do this on your calculator. The first one is going to be Q of 0. That's a 0. And we know that it's 2000 e to the negative 0.06 times 0. And that's just going to equal I'm trying to find a stylus here that will work for me. Okay, well, that's just going to equal to this, anything to the 0, right, is 1. So this is just equal to 2000. Oops. All right, so we have 2000 for the first one. And for the next one, we're going to have a 5 where the t goes. So I'm going to try to zoom this out just a little. Zoom to Control Y. That's the problem. Let's go to 150 or 140. Okay. So we're going to have 2000. Let's try this again. I don't know what I just did. Yeah, it's not working for me. I'm trying to do it a quick and easy way. It's not quick and easy. I'm gonna have to try again. It's not here.
It didn't work out. I was trying not to have me in it. I didn't want me in it. I wanted just the math. Okay. Guess I'm going to start again. Okay. These are the additional problems for topic 13. And the first one of those problems asked us to consider, let's see, I have to open it up. We're going to have a problem. So this is problem 1, where we're given a quantity, a mathematical model for a quantity that's 2000 e to the negative 0.06 t. And we're asked to, we're told that this is a quantity Q of t, and it exhibits this exponential decay, which we know because of this negative 0.06 t, and t is measured in years. So this is measured in years, and that's important for how we use this function in case we're asked to do something that's different than years. We might have to do a fraction of a year. So what is the decay constant? Well, the decay constant means that there's going to be a negative, and it's the number in front of the t. So if this is negative, it's decay. But the value really is this number right here that we are focusing on, and this is the k, which we call the rate constant. If the number is positive, a synonymous name for this is the growth constant. So this is k is positive, is the growth constant. And we kind of think of the whole thing when we're talking about whether it's positive or negative. If k is less than 0, it's called a decay constant. Okay, so here the question 1a is what is a decay constant? It's negative 0.06. What is quantities present initially? So remember, the number that comes out in front of the exponential is what we refer to as Q naught. So the general form of these equations, right, is QT equals Q naught e to the negative KT, where this is the initial quantity. So in this case, and that's because if you put in 0 for t, you'll see that e raised to the 0 is 1. And so this is what you get when time is 0. So we say that the initial quantity is 2000. Okay, then we're asked to fill out this table, which has got t and values of q. So this is like an XY chart. We're going to have 0, 5, 10, 20, and 100. All right, so for each of these, we're just going to plug the t into 2000 e to the negative 0.06 t. So putting in 0, we already know this is just going to be our initial quantity, 2000. Now to plug in 5, we're just going to say it's 2000 times e raised to the negative 0.06 times 5. And so that turns out to be 1480. I'm going to round to whole numbers here, 1482. So we went in 5 years, we went from 2000 to 1482. Now we put in 10, we just do 2000 times e raised to the negative 0.06 times 10. And now we get that this drops to 1098. And now if we multiply, now if we're going to go into the putting in 20, we're going to get that it's 2000 times e to the negative 0.06 times 20. And we see that now the numbers drop to 602. So we're dropped in 20 years from 2000 to 602. And now we're going to see what happens after 100 years. So putting in the 100. And this drops all the way down to 5. So it's pretty much gone almost after 100 years. Okay, so that's problem number 1. Problem number 2 is a growth bacteria. So here we're told that the growth rate of the bacterium E. coli is a common bacteria found in the human intestine and is proportional to its size, whatever. Under ideal laboratory conditions, when this bacterium is grown in a nutrient broth medium, the number of cells in the culture doubles every 20 minutes. Okay, so the way to interpret that problem, and I hope you have these problems open in front of you so you can read them yourself. So number 2, we're reading about that the key thing is that it says that the number of cells doubles. Now it could say triples, it could say quadruples, but when it says doubles, that means that it's twice, right? So that means 2 times the original amount. We're told that it doubles in 20 minutes. All right, so the first thing we have to do is, first we're told that if the initial cell population is 100, so the initial cell population, now remember in the back of your mind, whenever you have one of these bacterial or any kind of mathematical model for an exponential growth or exponential decay, what's in the back of your mind is you're gonna have to fill in all the missing pieces to the form initial E to the negative, or this one's growth, so it's gonna be positive KT. So we're going to have to figure out Q naught and K, just like when you have Y equals MX plus B and you have to solve for M and you have to solve for B. Here, you got to solve for Q naught and you have to solve for K. All right, so this says if the initial cell population is 100, so they gave us this. Determine the function Q of T that expresses the exponential growth of the number of cells of this bacteria as a function of time. Well, if that is what they're asking us to do, and they already told us that Q naught is 100, the only thing that's missing is the K. So how do we figure out K? The key is that we're told that the number of cells doubles in 20 minutes. What that means is that whatever this initial is, it's going to be double in 20 minutes. So in 20 minutes, it's going to be double. We don't know K, but we know that this is going to be measured in minutes. Right, so this is in minutes, and we're going to put 20 here. Okay, so now let me reread this question so you're really clear on what it's saying. It's saying if you start out with 100 and you plug into this exponential growth model, that has some unknown rate constant K, in 20 minutes, it's going to be 200 because it's double the initial, right? This is 2 times or double in 20 minutes. So now we have everything is filled in except there's only one variable. So we have to solve for K. Now, usually, or up until now, it's been we didn't really know how to solve for K, but now we do because we know how to use logs. So let's first of all, identify that the exponential is on this term right here. So let's get that by itself. So it's multiplied by 100. So we're going to divide both sides by 100 to get rid of any coefficients in front of the exponential term. So let me remove this. So we got 200 divided by 100. That's 2 equals e to the k 20. All right. So now what do? Well, you have a exponential here. Now we can use our log transformation formula, which says that the exponent, and I'm going to just write it, these are multiplied by each other, so I could just say 20k. So the exponent is equal to the log base e, so that's ln, of the value 2. So that I just did that transformation, and let me just put that aside on the side. So this was what we used to call it, right? We had b to the y equals x. So the b here is the e, the y is the whole package in the exponent, and the x is the 2. When we transform to logs, we say that the exponent is equal to the log base b of the value. So this is what you need to know to be able to do this problem, right? This is the key. So now that we've gotten this far, now it's just algebra, because now we're just going to divide both sides by 20 and solve for k. So k is approximately equal to the natural log of 2, which is on your calculator. So it's the natural log of 2 divided by 20. Make sure you can do this, because I get that this is approximately 0, 3, 4, 7. Now we're going to be doing problems that involve money before too long, and it's really important on some of those that we don't round. So right now we're rounding to 4 decimals, and that's okay because we're actually going to be counting number of whole cells. And when we start to get into really big numbers, we're going to just want to keep this as the natural log of 2 divided by 20. But for right now, this is fine. So now we have the answer to part A is going to be that the quantity is 100, the initial quantity, E, and our growth is 0.0347 times however much time there is. Now, just to be clear, this K never changes. So that's why when I put in 20 minutes and I put in everything else I knew that happened at 20 minutes, I was able to solve for the K. Like, think of it like the slope. No matter what X you put in, the slope is the same. It's the same thing with the K. No matter what time we put in, the rate constant is the same. So once I figure out what it is, I can go back to any time T. And now I have the mathematical formula for the growth of this bacteria. Now I'm ready to do anything that I'm asked to do with this function. And in particular, part B says, how long will it take for a colony of 100 cells to increase to a population of 1 million? So B is how long will it take, right? How long will it take? Okay, that just means solve for T. Right, so whenever you read that, that means solve for T. And what we want to know is how long we're going to solve for T under the conditions where the quantity at some time T, which we don't know, is going to be 1 million. And so we know we're going to start out with 100 cells. We're going to use the equation we figured out in part A, We're going to put everything we know in here except, and then what we're going to be left with, what we don't know is the t. So starting out, we're going to have 1,000,000 equals 100. Now I'm just copying the right-hand side of this. E to the 0.0347 t. Okay. All right. So now I divide both sides by 100 because I want to isolate. I want to isolate where that t is. So I'm going to divide by the coefficient in front of it to make it 1. So I'm going to divide both sides by that. Okay, I'm going to get rid of 2 zeros here, and I'm bring this down to 10,000. 1, 2, 3, 4, right? Is equal to e to the 0.0347 t. All right, now I'm going to do the same thing I did in the last problem. At this point, it's really repeating the same steps. We're just going to convert to the log. So the exponent, 0.0347 t. Okay, so that's my exponent. Is going to equal the log base e, which is natural log, of the value, 10,000. And then we're going to divide both sides by 0.0347. And that is going to give me t is equal to, or I should say it's approximately equal to, and we're asked, this was, remember, initially being asked in minutes. So we're going to round to the minute. Well, I think that's okay. If the problem doesn't tell you otherwise. So let's go ahead and do this. So we're going to have the natural log of 10,000 divided by 0.0347. So 265.4. I'm going to go 1 decimal minutes. So that's, think about that. So we divide that by 60 because we know there's 60 minutes in an hour. I'm just saying this is in a little bit over 4 hours. We go from 100 E. coli to 1,000,000 E. coli. That's what that's saying. That's pretty fast. That's why when people get sick with an infection, they can get very sick very quickly. Okay, so if the initial cell population was 1,000, how does this change our model? Well, very simply. If Q naught is 1,000, all it's asking you to do is rewrite the model with a different Q naught. So it's just 1,000 E. It doesn't alter the rate constant. The rate constant stays the same regardless of what the initial quantity is. Now you may say to me, yeah, but wait a second, we used that when we figured out how to double. Well, if I put the double here, it's going to be the same amount of time to double. So it's going to be 2,000 divided by 1,000, and that still will be 2. It ends up being mathematically the same. So your rate constant never changes once you have it figured out. Okay, so that's the answer for part C. Okay, the next question was resale value of Garland Mills. Okay, resale value is the topic. Garland Mills purchased a certain piece of machinery 3 years ago for $500,000. Its present resale value is $320,000. Assuming that the machine's resale value decreases exponentially, what will it be 4 years from now? Okay. So for problem number 3, we're told we have something that we're going to assume decreases exponentially. So that means we know that immediately this is what we need to figure out. We're going to need to figure out what Q naught is. It's decreasing, so it's negative KT. And we're going to need to figure out what the K is. So maybe I'll just put these. We don't know what Q naught is, and we don't know what the K is, but we have a negative because they told us that it's decreasing exponentially. Okay, so they purchased a certain piece of machinery 3 years ago. So we're going to say that 3 years ago, is t equals 0. So we're going to say that's when we started counting time, was 3 years ago, is t equals 0. And the initial amount that it was worth was, so initial value of the initial quantity it was worth was 500,000. All right, so let me read that again. If the, Garland Mills purchased a certain piece of machinery 3 years ago, so that also tells us that we're counting in time in years, for $500,000. We're going to assume the machine's resale value decreases exponentially. What will it be 4 years from now? Oh, its present resale value is 320. So present value. And we're going to say that's when t equals 3 because we're 3 years after the initial amount. Present value when t equals 3 is 320,000. Okay, so we're going to use what we know, what they give us, to solve for the k. Okay, so let's put this in. So we have 320k. That's our quantity, right? Present value. So this is going to be a quantity is going to equal this formula. We got to put the 500 over here for the Q naught. And I'm just going to not confuse you with the K's. Let's go ahead and put comma 0, 0, 0, comma 0, 0, 0. E times E, that's times E. And then in the exponent of E, we have this minus K times 3. Okay, so make sure that's clear. Because in 3 years, that's the present, because we're starting to time equals 0 was 3 years ago, so now it's t equals 3. We have negative k times 3, so we have all this. So now here is where our unknown is. Our unknown variable is k, and so we got to get rid of the coefficient in front of e. So let's divide both sides by 500,000. All right, so just divide this on the left side. And you get that this is 0.64 is equal, this just goes to 1, right? 1 times this, e to the negative 3k. I'm going to just flip that around so we have it in the normal way we're used to looking at it. Okay, so now we can just convert it over to the log world. So we're going to convert to log. Go to log. I'll say logs. Go to logs. All right, so we're going to take the exponent, minus 3k. And it's going to equal the log base e, which is the natural log of the value. All right, so now we can take this and calculate what the natural log of 0.064 is divided by the negative 3. And we find that we get that k is approximately 0.1488. And it's, I see 1487623, but I'm just going to round it to 1488. Okay, so now that we know this, we have what we need to solve for any time t. So time t, where t was starts 3 years ago, okay, is going to be this initial amount, so 500,000. E raised to the negative 0.1488 times t. Now we're asked, so this was the key step. We have to get this mathematical model that has both the Q naught and the K I solved for. Once we have that, now we can go on and ask any question about the quantity, or the time. We're asked in this problem, what will it be? What will the value be 4 years from now of this piece of machinery? Well, 4 years from now. So 4 years from now. Remember, now was T equals 3. So 4 years from now is Q at 4 plus 3, or 7. So we're going to put this in 500,000 e to the negative negative 0.1488 times 7. And that's in the exponent. So we're going to multiply this out and get 500,000 times e to the x raised to the negative 0.1488 times 7. And I get that it's approximately, and because we're dealing with money, we're going to round to the penny, 176,444.80. That's a 4. Okay. The next problem says, this is a world population problem. And it says the world population at the beginning of 1990. So we're going to start with 1990 was 5.3 billion. So this is question number 4. And it tells us that world population in 1990 was 5.3 billion. Assume that the population continues to grow at a rate approximately 2% a year. So rate growth of 2% per year. Okay, so what this is going to tell us, when you see 2%, this rate of growth of 2%, this is going to be, the K is 0.02. All right, so you remember how to convert a percent to a decimal. You move the decimal that's implied right here, 2 to the left, we get K equals 0.02. We know that we're talking, that our time is going to be measured in years. All right. So actually we're given everything we need now because we were given the Q naught, right? This is our Q naught, the initial quantity in 1990. So we're going to say T equals 0 is 1990. And then we have our formula that Q of T is going to equal 5.3 billion E raised to the 0.02 T. Okay. Using this function, complete the following table of values and sketch the graph of a function Q. All right, so there's a lot of numbers in here. I don't think I'm going to do them all. I'm just going to get you started. So we got year and population. 1990, and I'm going to suggest that between year and 1990, we're going to write T. So when the population is 1990, this is times 0. And we know that at that point, at time T equals 0, we put 0 in for T here. E raised to the 0 is 1. And that's our initial quantity, 5.3. Okay. The next one is 1995. Well, that's 5 years after 1990. So we're going to plug in 5 into this value for T. Okay. So it's 5.3 times E raised to the 0.02 times 5. And I get that this comes out to 5 point, and I'm going to round to 1 decimal, 9 billion. Okay, I'll let you continue this, but we'll go ahead and do one more. So in the year 2000, that's 10 years later, we're going to plug this in again. And same formula, but now we're going to put T as 10. And I get that this comes out to 6.5 billion. And I'll let you go ahead and continue to fill this out. And when you're done, what you're going to want to do is graph. So T is going to be on the x-axis, what's normally the x-axis, and we're going to count in billions. Start with 5 billion here for the world population, or Q, or quantity. And so I'm going to go put a dot here, 5.3. And let's say we're going to be counting, this is 5 years later. Let's say that's 6. We're going to be right here. And 10 years later, the year 2000, we're at 6.5. Oops. Right, and I'll let you continue that. What you should be seeing, if you do your math right, is an exponential growth function that's going to go up like this. Well, a little bit smoother. There we go. Okay, and the last problem, number 5, says, if the world population continues to grow at the rate of approximately 2% per year, find the length of time. Oh, so this is referring to the previous problem. So let's refer to problem 4. We already had that it was 5.3 billion e to the 0.02 t. So this was from problem 4. So for problem 5, we're told, okay, assume this rate continues. Find the length of time required for the population to triple in size. Okay, so to triple in size, we got to go 3 times 5.3. So triple in size. Oh, and by the way, let me back up here a little. It says find the length of time. So I have somebody cooking in the kitchen. If you hear a lot of sizzling, I think someone's making me a yummy dinner. So we'll just let that go. Okay, so find the length of time, T naught, for the world population to triple in size. So this is kind of pretty clear here that we're going to be solving for T. Now don't get thrown by this little T naught. They just mean a specific amount of time. So you're basically going to solve for T. When Q is equal to 3 times 5.3 billion. Right? This is what we mean by triple in size. Okay, so we can go ahead and write that. We want 3 times, this is a little bit of a shortcut. You don't have to do all the math to 3 times 5.3 billion. Now I'm going to plug into this formula, 5.3 billion e to the 0.02 t. Okay, so once again, I want to solve for t, which is my exponent. So I'm going to divide by the coefficient, which is 5.3 billion. Divide that on both sides. These cancel, these cancel. So after you've done a few of these, you'd realize this is Q naught. This is 3 times Q naught. And so you don't really have to do all the math. If it wants to triple, you just put 3 equals e to the 0.02 t. All right, now we just convert over to logs. So convert to logs. So the exponent, 0.02 t, equals the log base e, which is a natural log of 3. And then t is just a natural log of 3 divided by 0.02. And that's equal to 54.9. So the population will, and this is years, so the population will triple in 54.9 years. So that is less than one person's lifetime, average lifetime. Okay, and that's 5A. I just realized, I thought we were wrapping it up. That's 5A. Okay, and 5B says, okay, use the time T naught given in exercise 4. Using the time, what would be the world population if the growth rate were reduced to 1.8% a year? All right. I'm not sure why they mean using the time given in exercise 4. Oh, they must mean that T naught, that given the time T0. So what they mean is assume that we're starting to count in 1990. All right, so let's go ahead and look at this problem. So 5B is not well written. So if you get frustrated with that, I apologize. I try to only quiz you or test you on ones that are well written. We want to know using the time T naught. So they're saying T naught from exercise 4 is T naught means the initial time. And that's a little bit more advanced than we've covered, but that's what they mean. That's an idea that comes from physics and biology and chemistry and all that. Okay. So the initial time T naught is 1990. Okay. And so what we mean by this is that time 0. Okay, just like Q naught is the initial quantity. What would be the world population now is what they mean. The population now if the growth rate was reduced to 1.8% per year. So first of all, now is 2021. Right, so 2021 from 1990 is going to be 41 years. So this is T equals 41. No, I can't do math. 31.
30.
Okay, 31. So T equals 31. Find QT. We want to know the quantity now. So our formula that we're going to use is this 5.3 billion. So the Q naught stays the same. But instead now, or instead of 0.02, this is going to be 0.018, 0.018 T. Right? So this is Q at, in 31 years from 1990 is 5.3 billion. E to the 0.018 times 31. Alrighty, so we're going to go in and put 5.3 times e to the x raised to the 0.018 times 31. And we get that this is 9.2 or 9.3 billion. So this is saying that we have approximately, if this model is right, we should have around 9.3 billion people in the world today. And I haven't looked it up recently, so I'm not sure. Is that even close to right? Let me check that. World population 2021. 7.9 billion. So that's actually not accurate because right now, according to the World Population Clock, we're looking at 7.9 billion. So the rate must be even lower than 1.8% a year. So this is what I'm seeing. So we're a little bit off, but sometimes models aren't that accurate, but they can be helpful. You got to always know that the assumptions in the model may not always hold, but when we're going to be working with money and business functions that have very similar structure next, you'll find that they will hold because the bank is held, or whatever financial institution is held to the rates that they promise. Okay, thank you. Alan?
Yep.